Notes 4.3 part 2. In this set of notes, we will actually get into the mean value theorem, unlike from part 1, but we will also be looking at identifying local extrema using the signs of derivatives. So first thing that I want to talk about are critical points. Where do they occur? What do they look like? How do we find them? So critical points are going to occur where what happens? Where the derivative equals 0, or where the derivative does not exist. But keep in mind, we need those x values to exist in the domain of the function in the first place. So not every single scenario for where the derivative doesn't exist is going to work. We can't consider any sort of discontinuities. Infinite, vertical asymptotes, holes, none of those x values would actually exist in the function in the first place. So those types of scenarios are out. So visually, our derivative is going to equal 0. Where we have nice turning points. So basically at our local extrema. And then our derivative is not going to exist, but also still be critical points where we have corners, where we have, how do I get this into the next part? Let me think. Wanted to say vertical tangents, so I guess I can keep going like this. Or cusps. Really make sure that that vertical tangent looks like a vertical tangent. There we go. Next thing that I want to recall is how do we figure out where a function is increasing or decreasing? First thing that we want to do is find the domain of our function. This is essentially finding where our function is increasing or decreasing. We have to find the critical points. And finding the critical point starts off with figuring out the domain of the function. That way we don't accidentally say that a point is a critical point when it's not even defining the function in the first place. Then we want to create a number line with the missing domain values and any critical points. And then we are going to test values from each interval using our derivative function, because we're wanting to test the derivative signs. Because remember, where a function is increasing is going to be where the derivative is positive. And then where a function is decreasing is where the derivative is negative. So this is actually leading us naturally into something called the first derivative test. And I want to look up here to kind of see if you might notice something. Here I said that we have local extrema. This would be called a local minimum. What are the derivative signs before that local minimum? Negative. And then after that, pretend that was a nice tangent line, we have positive slopes. Oh, look, over here, I have a local minimum. Before that, I have negative slopes. After that, they're kind of shallow, but they are still positive slopes. Oh, look. Technically, we have a local minimum here. Negative slopes to positive slopes. It's not a coincidence. So anytime that we are looking for critical points, we could also very easily figure out when we're testing for increasing or decreasing intervals, hey, is that going to be a local max or a local min? So if our derivative changes from negative slopes to positive slopes, the output of the function at that critical point is a local min. There's your visual. And then conversely, if our slopes change from positive to negative, then the output at that critical point is a local max. We're also going to find another way to do this in, I don't remember if it's the next set of notes, but it will be coming up very soon, that we can find another way to see if we have local maximums or local minimums. But this is just one way that we could do this. So to summarize this process, to analyze our critical points using the first derivative test, we need to find our critical points, which also includes, you know, the domain. And then we test the signs on our derivative on the intervals between the critical points and your, well, just between the critical points. And then we use the first derivative test to see if we have local max or local min. So flipping to the next page, let's get into our first example here. We're going to analyze the critical points in the increasing, decreasing behavior. So when I say analyze the critical points, I mean, do we have local maxes, local mins, or neither? Because if I were to look at that critical point with my vertical tangent here on the front, that's not a local max, it's not a local min. The slopes beforehand were positive and after were positive, so there was no sign change. If that's the case, nothing's going on there. You need to have a sign change for it to be a local max or a local min. And then I want my increasing and decreasing intervals, of course. So let's get started. Hopefully it comes naturally at this point. Find that domain. The domain of a trig function is, if it's just sine and cosine, is always going to be all real numbers. There's no issue with plugging angles into cosine, no issue with plugging angles into sine. There's no division happening here. It's just my basic trig functions. It's all real numbers. So I don't have any issues in my domain. Second, we are going to take our derivative so that we can find our critical points. And I will say, even if there were issues in the domain, you'd still want to put those on your number line because the derivative values could change on either sides of discontinuities. You just kind of have to keep in mind which points are coming from domain issues and which points are coming from critical points when you test your number line later. Something that you might want to jot down. All right. Go ahead and take your derivative. So cosine is being squared, which means technically this first term is cosine of x squared. So I need to use chain rule. So that would be 2 cosine of x times the derivative of the inside, which would be negative sine x. And then the derivative of sine is cosine. I'm going to go ahead and clean this up a little bit. And because I know that I'll be solving later, I'm also going to take the opportunity to factor. So I see that I have a cosine in each of my terms, so I'm going to factor a cosine out. Factoring a cosine out leaves me with negative 2 sine x plus 1. There were 2 terms originally. There should be 2 terms in my parentheses when I just am factoring out a GCF. And keep in mind the interval that we are looking at critical points over. It's not 0 to 2 pi, it's just 0 to pi. So we have to keep that in mind when we are solving here. Critical points occur where the derivative equals 0 and where the derivative does not exist. I might need to move this later on, so just putting that out there now. So since I already have my function factored, I'm just going to actually set each factor equal to 0. Part of the reason why I factored that earlier. Okay, cosine equals 0 at pi over 2 and then 3 pi over 2, but that's not in our range, so this is it. This is also in the domain of my function in the first place, so this is a critical point. Solving this for sine, we got 1/2. So where does sine equal 1/2? Like I've said many times, I don't have the unit circle memorized, so I actually just kind of build it up. Sine is y, which means I'm looking for y values of 1/2. Okay, so it looks like it's at pi over 6 or 30 degrees and 5 pi over 6. The only reason I know that that one's 5 pi over 6 is because I'm going backwards pi over 6 from pi. So those are going to be the two angles. Those are both in my interval and they're both in my domain, so those are both critical points. Okay. Where does our derivative not exist? Like I said earlier, we have just sine and cosine. They're just being multiplied. There's nothing that would make this function or this derivative function discontinuous. So this is not going to create any critical points from where the derivative does not exist. So we found our domain, we found our critical points and tested them to look at the domain. Now let's analyze these critical points on our number line. I do want you to remember that we are restricting the interval that we're looking at. So we are going to cap it at 0 and pi. I think it's important that you recognize that because we don't want to go beyond pi. You don't want to accidentally plug in a number that's greater than 3.14, 159, 265, blah, blah, blah. I don't have any domain restrictions, so I don't need to put those on my number line, but I do have 3 critical points and I want to make sure that I put them in order. Pi over 6 is the smallest. Pi over 2 is the middle value, and then 5 pi over 6. It's right there. If you don't automatically know numbers in between these, you can get them in decimal forms and just plug in decimal values that are clearly going to be in between these or lying within these intervals. I don't know an angle that is smaller than pi over 6 from the unit circle, but of course I could use like pi over 12, or I could just get decimals. Make sure that you are in what mode in your calculator? Radian mode. And then let's go ahead and put our derivative function into our calculator. All right, so putting my derivative function into my calculator, we got cosine of x times -2 sine of x plus 1. Right, let me just double check that really quick. That way I'm not gonna make any mistakes later on. Looks good. Okay, so I'm going to first and foremost figure out the decimal version of pi over 6. So I think it's safe if I do half. And in my calculator, I have it set up so that I can just automatically plug numbers into my table. If you want to see how to do that, you just do second table set, so second window. And I have it set so that I can type in my independent variable. So I'll ask my independent variable and it'll automatically generate the dependent variable for me. Or of course you could do not second trace, alpha trace, and you could just pull up your Y1 menu. Okay. Or I could even do that in the table and get the same number. Something that's positive. So go ahead and do that for each of your intervals, and let's see if we're getting the same pattern. Pi/4 is definitely between pi/6 and pi/2. Negative. Number between pi/2 and 5 pi/6. Oh, 3 pi/4. And then I don't know, there's no angle between 5 pi/6 and and just pi. So I'm gonna look at what those decimals are really quick. Okay, so 3 would be a safe number that's between them. Okay, positive, negative, which is usually what's going to happen for critical points if they're anything other than a vertical tangent. So this is kind of what I would expect usually to happen. Also, since we didn't have any domain issues, which sometimes there could be the same slopes on either side of domain issues, this is generally what I expect to see when I only have normal critical points happening. So we have positive slopes to negative slopes. That means that pi/6 is a local max. Or f of pi/6 is a local max. Negative slopes to positive slope, local min. But you know what? I'm gonna leave these up here. Maybe in a different color though. Okay, so let's go ahead and write up our answer. I do actually want to know what the local max and local min values are. So I would like you to figure out what f of pi/6 is, what f of pi/2 is, and what f of 5 pi/6 is. And you can just round that to a few decimal places, or like 2 decimal places is fine. I'm going to go ahead and stop my writing and just put the answers up here in 3, 2, 1. I actually realized it'd probably be a good idea to do some of these numbers together. So I put my function in and I'm going to go ahead and get my outputs here. Okay, so it looks like we have 1.25 as the 2 local maxes and then 1 as our local min. And then we were also asked for our increasing and decreasing intervals. So we are increasing on the positive intervals, decreasing on the negative intervals. So 0 to pi/6, union pi/2 to 5 pi/6. Decreasing on the opposite intervals. And here is our nice long answer. Now let's get into example 2. Example 2 says analyze the critical points of g of x using the graph of g prime. So first and foremost, go ahead and find our derivative values. I'm sorry, our critical points. You don't need to find your domain here. I know the domain exists everywhere here because I don't see any discontinuities. And if our function is differentiable, it is therefore continuous. That is a theorem that we learned back in the beginning of chapter 3. So we have the derivative equaling 0. I'm going to cross this one off because that's not happening anywhere here. Our derivative is continuous. So our derivative function actually has outputs of 0 at 1, 3, and 5. Because this is the actual derivative graph. We're looking at where it equals 0, where our outputs are 0. So let's analyze each of these. I don't know the outputs for g of 1, so I can just say that g of 1 is going to be, see, we have positive outputs to negative outputs. So our graph would have positive slopes to negative slopes. That would be a local max. G of 3. I already know the slopes before that are, oh, the slopes, I'm sorry, the outputs. Looking at outputs because I have G graphed here. So I already know that those are negative outputs going to positive outputs. That would be a local. Negative slopes to positive slopes, local min. G of 5. The outputs for G prime are positive to positive. So G of 5 is neither a max or a min. So what I would expect my graph to probably look like there would be some sort of vertical tangent, or I could actually have a critical point like this. Momentary slope of 0, positive slopes to positive slopes. So I wouldn't expect that to be a local max or a local min. Okay, so we are done talking about critical points and analyzing them. I would like to go ahead and get into the mean value theorem. So the mean value theorem states that if a function is continuous on a closed interval, criteria 1, and differentiable on an open interval, criteria 2. And I'd like to remind you that we've been dealing with these criteria a lot lately, like with the with Rolle's theorem that told us that we can guarantee that a derivative. Oh, Rolle's theorem had another criteria, so we're not quite there. The extreme value theorem dealt with continuous on a closed interval, guaranteeing that we have a max and a min. So I'll just keep going. A little sidetracked there. So if it's continuous on a closed interval, differentiable on the open, then there exists at least one C value, so one X value, such that the derivative at that point will equal the slope of the secant line connecting the endpoints, which the slope of the secant line connecting the endpoints would be the change in those Y value outputs over the change in the X value out, or just the X values. Can you guys remind me, what does the derivative represent visually? Hopefully you said the slope of the tangent line. So this is basically saying that the slope of a tangent line at some X value in the interval will be the same as the slope of the secant line over that interval. So if these two lines have the same slope, what's their relationship? Lines that have the same slope are parallel. So I'll expect a tangent line and a secant line to be parallel. I'm going to go ahead and draw an example. I would like that to be a little bit more drastic. Hold on. There we go. So I'm going to do, let's do black lines. Of course, it's purple. Here we go. Okay, so that would be our secant line. And then give me 1 second, I'm going to copy this. And then I'm going to figure out, whoops, where there's an X value in that interval that has the same slope just by like testing it out. So, oh, there we go. About right here. Come on, line up. Okay, perfect. Now there could be multiple values within the interval that have the same slope as that secant line, but I can guarantee that there's at least one using the mean value theorem. So in this last example, I'm sorry that it still says example 1, should be, I think, example 3. We are going to verify the mean value theorem on this interval. So when I say verify, remember, we are checking the criteria before we find the X value that would meet the conclusion. So first and foremost, is F continuous on our closed interval? Figure out the domain. That'll help us figure out if there's any domain issues in our, or discontinuities in our interval. With our function, the only issue that we're going to have is in the denominator. So if we have x plus 2 equals 0, that's going to cause a domain problem. So basically, x cannot equal -2. -2 is not in our interval, so we are all good. Let's go ahead and see if our function is differentiable on our interval, which just again means is our derivative continuous on that interval, but the open one. So we'll figure out the derivative first and then get its domain. Low, d high, derivative of the numerator, which is 1, is going to be 0, minus high d low over the square root of what's below. So this basically disappears that first term, and we just have -1 over x plus 2 squared. Our domain of the derivative is going to be the same thing. Same kind of scenario happening in the denominator. So we are good. Our function is differentiable on that interval. Okay, so our two criteria are satisfied. Let's go ahead and verify the mean value theorem. So we are going to see what x value is going to give us the slope of our secant line. we're gonna figure out where f prime of x equals f of 7 minus f of 3 over 7 minus 3. Replacing f prime with what the derivative actually is. And then f of 7, that would be 1/9 minus 1/5 over 4. Just to save time, I'm going to put that in the calculator and simplify this. Meant to do that after. Oh, wow. Come on, Miss Sandor. You know how to use a calculator. Okay, -1 over 45. I'm going to go ahead and cross multiply to solve this. We can drop the negatives on both sides. And in fact, you know what? I'm just going to solve the rest of this and you'll see the answer appear in 3, 2, 1. Here are the two solutions. Now remember, we are verifying the mean value theorem on the interval from 3 to 7. So this is actually the value that is going to verify it. So I'm going to write a little sentence that x equals 4.708 verifies the mean value theorem for f over 3 to 7. And that is it. Notes are done. If you have any questions, make sure that you ask.